Hey there and welcome. Today, we are going on a mission to crack a secret language, one that scientists use every single day. We're going to decode this system for naming chemical compounds, and I promise, by the end of this, you'll be speaking chemistry like it's your first language. You've seen these formulas everywhere, right? On food labels, in science class, maybe even on the back of your shampoo bottle. We all know NaCl is salt, and H2O is water. But how do we get from that jumble of letters and numbers to an actual name? What's the secret system? Here's the game plan. We're going to tackle this in 4 simple parts. First, we'll uncover the one simple secret behind everything. Then, we'll meet the 2 big families of compounds. After that, we'll put our skills to the test. And finally, we'll look at the one big exception, acids. Let's get cracking. Okay, section 1, the big secret. And I want you to forget about memorizing hundreds of random names. Chemical naming isn't about memory, it's about following a super simple logical code. And here it is, the entire, seemingly complex world of chemical names. It all boils down to answering just one question. Which of the 2 families does this compound belong to? You get that right, and honestly, the rest is a piece of cake. So, let's meet these 2 families. On one side, we've got team ionic, and on the other, we have team molecular. Pretty much every compound you're going to run into will fall into one of these 2 camps. First up, ionic compounds. Think of it like this. These are formed when a metal teams up with a nonmetal. The metal actually gives an electron away, and the nonmetal takes it. So you get a positive and a negative charge, and you know what they say, opposites attract. That creates a strong bond. The key thing to remember is right there, metal plus nonmetal. And the second family? Molecular compounds. These happen when 2 or more nonmetals get together, but instead of transferring electrons, they share them. The most important rule here, it's nonmetals only. Okay, pay attention, because this slide has the single most important rule of the entire system. Look at the left. For ionic compounds, we do not use prefixes. But on the right, for molecular compounds, we always use them. That is the core secret. And it's because nonmetals can combine in all sorts of ways, like CO is carbon monoxide, but CO2 is carbon dioxide. The prefixes tell us exactly which one we're talking about. Ionic compounds don't need them, because their charges lock them into just one specific ratio. All right, that's enough theory. Let's actually see this code in action. It's time to play the naming game and put our brand new skills to the test. We're just going to follow this simple 3-step process every time. First, figure out what the elements are. Second, decide which of our 2 families the compound belongs to. And third, apply the right rule. Easy enough, right? Let's do it. First one up, a compound made of carbon and oxygen. If you have a periodic table handy, great. If not, just follow along. What do you think? Okay, let's follow our steps. Step 1, identify. Carbon is a nonmetal, and so is oxygen. Step 2, classify. Well, 2 nonmetals together means this compound is molecular. And what's the rule for team molecular? We have to use prefixer. And here we can see that rule in action. If the formula is C2O4, the 2 for carbon becomes the prefix di, and the 4 for oxygen becomes tetra. Slap them together and you get dicarbon tetroxide. See? The formula literally spells the name out for you. Let's try another one. This time we have a compound made from potassium, that's symbol K, and nitrogen, symbol N. What family does this one belong to? Let's run the process again. Step 1, potassium is a metal, nitrogen is a nonmetal. Step 2, a metal plus a nonmetal makes this an ionic compound. So for step 3, what's our rule? Exactly, no prefixes allowed. And would you look at that? The formula is K3N. Even though there's a 3 there, we don't say tri-potassium. Why not? Because it's ionic. We just ignore the numbers in the name and call it potassium nitride. See how different that is from our last example? It all comes down to the family. Now for our last, really quick section. There's one group of compounds that kind of plays by its own rules, the acids. They're a special case, but luckily they follow a pretty clear pattern too. So how do you spot an acid? It's easy. Just look for 2 clues in the formula. First, it's going to start with H for hydrogen. And second, you'll see AQ at the end, which just means it's dissolved in water. If you see both, you've got yourself an acid. The formal name is simple, aqueous hydrogen plus whatever the other part is called. So HClAQ becomes aqueous hydrogen chloride. And this pattern works in reverse too. Now, you might see more common names like nitric acid, but the key takeaway is that an acid name always corresponds to a formula that starts with H and is dissolved in water, that AQ symbol. It's just another piece of the chemical code. So let's wrap this all up. The entire code comes down to asking one simple question. Is the compound ionic? A metal plus a nonmetal? If yes, no prefixes. Is it molecular? Just nonmetals? If yes, you gotta use prefixes. And acids are just that special pattern to keep an eye out for. That's it. You know, I love this quote by the physicist Jean Perrin, and it's exactly what we did here today. We took a system that seems incredibly complicated on the surface, and we boiled it down to one simple question and a few clear rules. You now have the key to a fundamental piece of chemistry's secret language. So my question for you is, what's next? Now that you can read the language of molecules, what other scientific codes are you ready to go out and crack? Thanks for joining me today.